All right, let's talk about 2.5. 2.5 is about the derivatives of the trig functions. And these are a lot of fun, I think. But they do require you to do a little bit of memorization, okay? But here we go. So to start off with, the derivative of sine is cosine, which is kind of nice, right? But here's how we know. Here's how we know that. So by definition, the derivative of the sine function would be limit as h approaches 0 of sine of x plus h minus sine of x divided by h, right? So that's just from the limit definition. Now, sine of x plus h, we have a sum formula that allows us to take arguments that are sums and rewrite them as products this way. So sine x plus h is the same thing as sine x cosine h plus cosine x sine h. And I'm not going to prove that formula to you. That's what a trig class is for, right? So you should take, if you're confused about that, you should take a trigonometry class, and your trigonometry instructor will explain it to you. But if you're in calculus, I trust that you've all had trig already. Anyway, so this whole mess down here is just sine of x plus h. And then the minus sine x and the h come along for the ride. Now, if we rearrange the terms a little bit, move the negative sine x here, then from these first two terms we can factor out a sine x, and we'll be left with cosine h minus 1. And from this last term, well, we just leave it alone, but then we're going to split the fraction up. We're going to put the h under this first group and the h under that second group, and then we're going to distribute the limit to each of those groups. So we have limit of this thing plus limit of this other thing. Now the sine x we can take out because it doesn't depend on h, and the same thing with the cosine x. We can take it out because it doesn't depend on h. And what we end up with should look pretty darn familiar. We talked about these two things, right, in great detail. Like we had almost an entire section about these two things back in chapter 1, right? But limit as h approaches 0 of this thing is 0. Limit as h approaches 0 of this thing is 1. So it's just sine times 0 plus cosine times 1, and that's just cosine. So skipping from the first step to the last step, the derivative of sine is cosine. So with that in mind, it's probably not surprising to know that the derivative of cosine is sine, except that here we have a negative sign, right? So be careful, right? Derivative of sine is cosine, but derivative of cosine is negative sine. And I'm not going to prove that one to you. It's left as an exercise to you to prove it if you want. But let me give you some examples of this in action. Okay, so let's find dy dx if y is x sine x. We're going to use the product rule from the previous section to do this, right? So if I think of x as f, and if I think of sine x as g, right, the derivative is going to be f times g prime plus g times f prime. So it's f times g prime, right? Derivative of sine x is cosine x, plus g times f prime. Derivative of x is 1, right? So this is f g prime, g f prime. Okay, we can clean that up a little. X cosine x plus sine x is the derivative. Alright, so there's that one. Let's do another one. Excuse me. Let's do y equals sine x over 1 plus cosine x. Go ahead and give the video a pause and see if you can figure this one out on your own. Okay, here's my solution. This time we're going to use quotient rule. we're going to do low d high, so derivative of sine x is cosine x, minus high d low, so derivative of the denominator, well, derivative of 1 is 0, and derivative of cosine is negative sine. So this is low d high minus high d low over low squared. We can simplify a bit. This is cosine x plus cosine squared x. Negative and negative cancel, so we have plus sine squared x over 1 plus cosine squared x. Or sorry, 1 plus cosine x squared. My apologies. But now cosine squared plus sine squared is just 1. So this is, this is really nice. So this is cosine x plus 1 over cosine x plus 1 squared. I just rearranged the terms down there in the denominator, but I did that to make it absolutely crystal clear that this is the same thing as that. So you can cancel off one of them, right? And you get 1 over cosine x plus 1. Ooh, I love it. I love it when things simplify nicely. Okay, so there's that. What about the rest of the trig functions, though? So here they are in all of their glory. These are the derivatives of the trig functions. Okay, derivative of sine is cosine. We've already talked about that. Derivative of cosine is negative sine. We've talked about that. But then derivative of tangent is secant squared. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. And derivative of cotangent is negative cosecant squared. You might have to make some flashcards to memorize these. So, do whatever you have to do to memorize them. But also notice that there are some similarities here. Secant and cosecant, for example, have very similar formats. Okay? This one's negative and this one's positive. This one is the co-functions, whereas this one is like the parent functions, I guess, if you want to call them that. Okay, secant tangent, cosecant cotangent, right? But this one's negative. So just like with sine and cosine, how one of them's positive and the other one's negative. And then tangent and cotangent are also very similar, right? Tangent is secant squared, cotangent is cosecant squared, except it's also negative, right? So you have this thing where all of the co-functions end up negative, right? The derivatives of the co-functions all end up being negative. And then you have the reciprocal functions, which are similar, right? Tangent and cotangent have similar derivatives. Secant and cosecant have similar derivatives. So it shouldn't be too terrible to memorize these, and you're going to have to. You're going to have to memorize these. Okay. Now, as far as the proofs are concerned, the proofs are really pretty simple. Because we already know sine and cosine. We already proved those. Or at least we proved sine. Cosine is similar, right? So if we wanted to prove what the derivative of tangent x is, we could say, well, derivative of tangent x, tangent is just sine over cosine. Right? So the derivative of tangent is just the derivative of sine over cosine. And now we can use the quotient rule on this. Right? This would be low d high minus high d low over low squared. And if you simplify that, cosine times cosine is cosine squared. Negative sine times negative sine is positive sine squared. Cosine squared plus sine squared is 1. So you just get 1 over cosine squared, which is just the same thing as secant squared. So sure enough, derivative of tangent is secant squared. The others are similar, right? You just write them in terms of sine and cosine, since you know what sine and cosine are already, and then you can prove them. Or like in this case, to do cotangent, since you already know what tangent is, you can just use the fact that cotangent is 1 over tangent to derive that one. So, okay. So let me give you some more examples. This time using some different functions, I guess. Let's find f double prime of pi over 4 if f of x is secant x Okay. Well, in order to find f double prime of pi over 4, first I need to find f double prime of x. In order to find f double prime of x, I need to start by finding f prime of x. So let's start there, f prime of x. If f of x is secant x, then f prime of x is secant x tangent x. Right? Okay. So that's f prime. So now f double prime is the derivative of f prime. So we need to derive this thing, or differentiate this thing now. So I'm going to think of this as f and g. I'm going to do f times g prime. So derivative of tangent is secant squared plus g times f prime. Derivative of f is secant tangent. Okay, so we can do a little simplifying. This is secant cubed plus secant tangent squared. Okay, so there's f double prime of x. So now finally, if I want f double prime of pi over 4, well then you just plug pi over 4 into x in each of these places. So let's see, secant 1 over cosine, root 2 over 2. So secant of pi over 4 is root 2, right? So this is root 2 cubed plus root 2 times tangent of pi over 4 is 1 squared, right? Okay, so that's, you know, root 2 cubed would be square root of sorry, I don't know why I don't know why I just blanked out, but we can put root 2 cubed. Oh, that's interesting. So root 2 times root 2 times root 2. Oh yeah, that's root 8. Okay, that's 2. I'm sorry. Or that's, no, that can't be right though, can it? Root 2 times root 2 is root 8. That's 2 root 2 is what it is. I was confusing myself with the exponent here and the index there. For some reason I was thinking cube root of 2 cubed, which would be 2. That's what was throwing me off. But no, it's the square root of 8. Square root of 8 is 8 is 4 times 2. Square root of 4 is 2. So it's 2 root 2. Okay, 2 root 2 plus 1 times root 2. Oh, that's kind of nice, right? So this is just 3 times root 2. There you go. Okay, so there's that one. And then one more example from this section. So you could have some application problems start to show up here. So this third one says, an airplane is flying on a horizontal path at a height of 3,800 feet. At what rate is the distance s between the airplane and a fixed point on the ground, P, changing when the angle of elevation from P to the plane is theta equals 30 degrees? So in other words, right, we've got this plane, it's traveling 3,800 feet above the ground. We've got some point on the ground, and then s is the distance from this point to the plane. And we want to know how quickly is that distance changing when the angle here is 30 degrees. Okay. Let me grab a fresh sheet of paper. Okay, so I'm going to take this picture down here, and I'm just gonna draw the right triangle. That's really the important part, right? Okay? So this is the scenario. And so I need to figure out a way to relate theta to this distance s. Well, I could use a trig function for that, right? So in particular, I could say sine theta is opposite over hypotenuse, right? So sine theta is 3800 over s. Okay. Now, I want to figure out the rate at which s is changing. So, so I should solve for s. If I solve for s, that'll give me the distance, right? That'll give me the distance. And then if I want to see how fast that distance is changing, I should take the derivative of it, right? So let's solve for s. So we get s equals 3800 over sine theta. Or if you like, you can call that 3800 times cosecant theta, because 1 over sine is cosecant, right? So, so I like that. I've got s equals 3800 cosecant theta. So now to figure out how fast theta, or how fast s is changing, I should take the derivative, right? I should look at the rate of change. So I'm going to say s prime of theta is going to be 3800 times the derivative of cosecant theta. So what's the derivative of cosecant? It's negative cosecant cotangent. Okay, so there we go, right? So this is negative 3800 cosecant cotangent. That's s prime of theta. Now the question is, at what rate is the distance changing when the angle of elevation is 30 degrees? So when theta is 30 degrees. So now I just go back and plug in 30 degrees for theta. Okay. Oh, cosecants and cotangents. Cosecant is 1 over sine, right? And sine of 30 degrees is 1/2, so cosecant is 2. Cosecant of 30 degrees is 2. So this should be negative 3800 times 2. Cotangent of 30 degrees, oh, okay. So cotangent, see, some of you are better at trig than me, I think. But cosecant, or cotangent is cosine over sine. Cosine of 30 degrees is root 3 over 2. And sine is of 30 degrees is 1/2, as we just finished saying. So root 3 over 2 divided by 1/2, that should just be root 3. Okay, so it's root 3. Goodness gracious. I should just use my calculator. I'm going to have to use it to get an approximation now anyway. So let's see. Negative 3800 times 2 times square root of 3. Well, so of course that's negative 7600 root 3, which is approximately negative 13,163.6. And I guess we should give some units of measurement, right? So s was, or the horizontal distance was given in feet. That means we solved for s in feet. So this should be feet per degree, I suppose, right? Okay. All right. So that's that one. Okay. Yeah. Sorry, I was just trying to think that through a little bit more, but that's that. So that's all I have to say for this section.